It's my great pleasure to introduce Dr. Jeff Schouneau, PhD. He's a professor in the Department of Soil Science at the University of Saskatchewan. He holds the Saskatchewan Ministry of Agriculture Soil Nutrient Management Chair in the College of Agriculture. He's Saskatchewan born and completed his undergraduate and graduate degrees in the College of Agriculture at the University of Saskatchewan. His research, teachings, and extension activities deal with soil fertility management, conservation, and nutrient cycling. He also owns and operates a grain farm with his wife Lynn near Central Butte in south central Saskatchewan. Ladies and gentlemen, Dr. Jeff Schouneau.
Great. Thanks a lot, Ernie. Fairly small crowd, and that's great. As I go through my presentation, if anything comes to mind, any thoughts, any questions that you have, please don't hesitate to shout those out, and I'll do my best to try and address them then. And I'm also going to leave some time at the end as well. Yeah, my background is in soil fertility, nutrient cycling, and plant nutrition, and I have to say that my main emphasis of my work, folks, has been on field crop fertility and nutrient management, and so the whole greenhouse industry, and indeed even vegetable production is something that's a little bit new to me, and I haven't done a lot of research work in myself, like what others like Doug Water have done at the university, but certainly I think I see this as something that's important, and certainly an emerging area, and something that I'm interested in doing more research work in the future as this industry grows here in Western Canada, and indeed here in Saskatchewan. So what I intend to do, folks, over the next few minutes is to talk a little bit about nutrients, and of course their very important role as the foundation of plant nutrition and plant growth. And I hope that some of what I talk about can kind of provide a good overview for some of the things that Dr. Misra is going to talk about specifically when it comes to fertility management in greenhouse production, in vegetable production, a little bit later on this morning. So I guess we go right back to basics, and we think about what plants need. Of course, they need heat and they need sunlight. Very critical, of course, for that good old photosynthesis process in which carbon dioxide is fixed into organic carbon. And the other very important constituents that we have, of course, the water that cools the plant, that transports the nutrients to the roots. The roots themselves require oxygen, very, very important, and so do the microorganisms. The microfauna, the macrofauna that are present in that soil need air to breathe. And the final part of that picture that's very important are the nutrient elements. And of course the soil or the growth media plays a very, very important role in the majority of situations, apart from hydroponic systems, in really regulating the water, the oxygen supply, and those nutrient elements. And we think about nutrient elements in general, folks, there's actually 21 what we call functional nutrient elements. And of those 21 functional nutrient elements, we've got 17 that we consider to be essential. Absolutely essential, meaning that the plant must have them to complete its normal life cycle. It can't be substituted by anything else, and it must be directly involved in the nutrition, the metabolism of that plant. And those are the ones that we normally maybe think of, those 17 essential elements. But there are another 4 elements out there that are required by some plants. So we can't really call them essential in the strictest sense of the word, but we do need to be aware that there are some other elements that may be required by certain plant species. So I'm going to take a little bit of a closer look at these functional nutrient elements, folks. So when it comes to essential elements first for all plants, we cannot forget about carbon, hydrogen, and oxygen. And the majority of the plant mass, folks, is made up of carbon, hydrogen, and oxygen. In fact, on a dry weight basis, about 50% of the dry weight of a plant is made up of carbon alone. And you throw in hydrogen and oxygen, they probably comprise as much as 95 to 97% of the total dry weight of a plant. That's water gone, so dry weight, 97% of the plant weight is made up of carbon, hydrogen, and oxygen. So we recognize those elements, folks, really as being the kind of backbone of all organic molecules. Sugars, starches, carbohydrates, fats. It's that carbon, hydrogen, and oxygen that provides the backbone. And of course, the carbon comes from photosynthesis, CO2 from the air. Hydrogen and oxygen come in with carbon dioxide and water. Now, normally we don't think too much about these in terms of being a supply that we can manipulate, because basically the carbon dioxide concentration is fixed in the air, right? But I do point out there has been some interesting work showing that when you enrich the air with carbon dioxide, in fact, you can increase the growth rate. And actually some experiments that were done to do this were actually done in greenhouses, where they increased the CO2 concentration, and that actually increased the rate of photosynthetic fixation. Now, I don't know what the practical or commercial applications of that are, but it was just something that I was thinking about as I was putting this presentation together. That perhaps in a greenhouse, that may be one place where you can actually do a little bit of control of that input carbon dioxide for photosynthesis. But normally not limited to supply, normally not something that we can do much about. These two elements here, nitrogen and sulfur, play a lot of important roles in the plant. But the two that come to my mind, I think, that we really need to be cognizant of is their role in the production of amino acids, which of course are the main building blocks of proteins. So in order to get appropriate protein quantity and quality in what you're growing, you have to make sure that you have an ample supply of both nitrogen and sulfur. Sometimes people forget a little bit about sulfur, but in fact sulfur is an essential constituent of 3 amino acids: cysteine, cysteine, and methionine. So if you don't have enough sulfur, you still may get some proteins formed, but you don't get the optimum formation of proteins. You may not get all of the proteins you need to maximize the yield and the quality of that crop. So that's why I often call sulfur the forgotten macronutrient, but very, very important. Nitrogen as a mineral nutrient, it's the nutrient element that's needed in the largest amounts, of course, typically constituting anywhere from 1 to 5% of the dry matter weight. And the nitrogen concentration of the plant material is directly related to the availability of nitrogen in the growth medium, whether it's a hydroponic solution or a growing medium, some type of a peat soil mix or pure soil. The concentration of nitrogen in the plant will very much reflect what the availability of that is in the growth medium. And that's why I'm going to stress a little bit later how useful a tool tissue testing can be in fact, monitoring the nutrient supplying status of your growth medium or of your hydroponic solution. Because I think I can say not only for nitrogen, but in general, the concentration of an element in plant tissue is very closely and generally directly related to its availability in the medium. Nitrogen, I would say, is often the most limiting nutrient out there. Sulfur requirement compared to nitrogen is about 10 times lower. So sulfur concentration would probably be in dry matter tissue 0.1 to 0.5%, whereas nitrogen would be about 1% to 5%. And in fact, sometimes people look at the ratios of nutrient elements in plant tissue, for example, the nitrogen to sulfur ratio, to determine if they have a balanced availability of nutrient. Cruciferous plants, cabbages, I'm most used to canola and rapeseed, but cabbages, cruciferous, brassicate crops have quite a high requirement for sulfur. So generally for those crops, we like to have a nitrogen to sulfur ratio somewhere around maybe 7 to 1. Whereas some other plants, for example, legumes, cereals, those types of monocots, the N to S ratio is optimum, is somewhere typically maybe around 10 to 1, 12 to 1, reflecting the fact that those plants don't require as much sulfur relative to nitrogen. So nutrient balance you can tell a lot about by looking at the ratios of nutrients in the plant material. Now nitrogen, taken up by the plant, absorbed by root spokes in the form of ammonium and nitrate. Now sometimes people generally just think about nitrate as being the only plant available form of nitrogen. But most plants, a lot of plants out there can take up ammonium as well. In fact, some plants that prefer acidic environments, and I'm thinking here, for example, of blueberries, also some conifers, that evolved in acidic environments actually tend to have their nitrogen in the ammonium form. Whereas some other plants, like tomatoes for example, they actually tend to have their nitrogen supplied to them in the nitrate form. But most plants can use both. Sulfur, it's absorbed by the roots in the form of sulfate. That's the plant available form. That's the ionic form of sulfur that's available. Now, legumes, as we know, they're a little bit different. Because what legumes can do is they can fix nitrogen from the air. A process I'm sure you're well aware of that can be carried out by legumes like peas and beans. And any legume will develop nodules on its roots. And those nodules are the home for a bacterium called rhizobium. And rhizobium will fix nitrogen from the air. The air is 78% N2, so there's lots of nitrogen in the air. Those legumes and those nodules that have that bacteria will fix that nitrogen from the air and supply it to the plant. So legumes can grow with little or no available nitrogen, that is like nitrate or ammonium, in their growth media, provided that they can develop those nodules and fix that nitrogen from the air. And so that's one of the real great things about legumes, in my opinion, in terms of them being very sustainable as a plant, as a crop, is that they don't need nitrogen fertilizer if you can get this fixation established. And sometimes that means inoculating your legume with a rhizobium bacterium, an appropriate species that can carry out that fixation. Interesting thing about legumes as well is that if you do supply a lot of nitrogen in the available forms of nitrate and ammonium, the legume will do fine, it'll grow well, but it won't fix the atmospheric nitrogen because it's kind of lazy. There's lots of available nitrogen to that legume plant, it'll simply say, hey, I'll use the available nitrogen, and it won't send any food to those bacteria in those nodules. And so the way to get the maximum amount of nitrogen derived from this fixation in those legume roots is actually to grow them in a media that is low in available nitrogen. Moving on a little bit, phosphorus, an element. We hear lots about phosphorus these days. People talk about phosphorus being a nutrient in our global environment, which is of a finite supply because it's mined out of the ground. And also it's an element that is of special environmental significance because of concerns of phosphate that's washed off the surface of agricultural lands into water body where it promotes algal growth and what we call eutrophication of a lake or a stream or a river. Phosphorus, I guess in terms of what it does in the plant, I like to think of it as being really the energy currency of life. It's needed in about the same amounts as sulfur, so phosphorus requirements relative to nitrogen, about 10 times lower, and absorbed by the roots in the form of the orthophosphate ion from the soil water bathing the roots. So it's the orthophosphate form that is the form that plant roots can absorb directly. And the neat thing, I think, about phosphate is that it is a very sticky nutrient ion. Sticky meaning that it tends to become adsorbed onto the surface of anything in the growth medium, whether it's a humus molecule, whether it's a clay particle. Phosphate is what we call immobile in soil or in a growth medium. It'll tend to stick on that surface and stay where it's put. And in some soils, some growth medium, if they're very, for example, calcareous with lots of carbonates in there, that phosphate may get stuck so strongly that it's not available to the plant. But if you're producing your plants in some media or hydroponics, if the phosphate doesn't have any minerals to react with, it will stay in solution. And that renders it highly, highly available. Potassium, moving down the list here, is what we call the water regulator of plants. And so plants that are deficient in potassium, folks, are particularly susceptible to water stress, to drought stress. And the reason why plants that are deficient in potassium, with the elemental symbol K, the reason why plants that are deficient in potassium are susceptible to moisture stress is because potassium actually controls the opening and closing of the little holes on the leaves, the stomata, that allow the carbon dioxide in for photosynthesis and regulate the water lost from the leaf through transpiration. So if you don't have enough potassium, those guard cells can't open and close properly, the plant can't regulate water very well, and it will be more susceptible to water stress. The other thing that potassium imparts in a lot of plants is it imparts stem strength. The ability of that plant to stand up straight, I should say, to resist falling over. So potassium is very important in that regard as well. And potassium, in fact, is certainly a macronutrient that's needed in quite high amounts. Needed in amounts only second to nitrogen. So for many plants, the requirements for potassium are just about as high as they are for nitrogen. So on a dry weight basis, you might find typical potassium concentrations 1 to 3% of the dry matter weight. It's absorbed as a cation, potassium, from the soil water. And like phosphorus, potassium is not highly mobile in soils or in the typical growth media that you might be using, like a peat soil mix or a peat mix in a greenhouse. Because phosphorus and potassium also tend to stick in the soil, as I said, they're not highly mobile. They also will not tend to readily leach out of the soil or the growth media compared to nitrate. Nitrate is really mobile. It doesn't stick in the soil. So it moves around with water. So if you have water moving through your growth media, through your soil, and that water's coming out the bottom, it's carrying nitrate with it, but chances are it's not carrying much phosphate or potassium. That P and K tend to stick in the soil. Also, the mobility of those different nutrients has some implications, folks, too, in terms of how a restricted rooting volume, like in a pot or a little growth cell, how a restricted rooting volume will affect the availability of nutrients. And because phosphorus and potassium are not highly mobile, effectively the root depletion zone for those nutrient elements is quite small. The roots can only take up phosphorus and potassium that's really close, that is, within a few millimeters of the root. Whereas in the case of nitrate, it can be a long, long ways away from the root, and it'll still get there with the water flowing to it, because it isn't stuck in the soil. Now, the practical implications of that, folks, in terms of rooting volume, is that when you restrict the root volume to a plant, that will tend to induce a nitrogen deficiency much more severely than it will a phosphorus or a potassium deficiency. So when you restrict those roots, probably the first thing that you're going to see suffer is nitrogen and also sulfur availability, because they have a big depletion zone, and when you cut that down and you shrink that up, that has a big impact on reducing what's available, because out there in the field, those plants take a big volume. They explore a very large volume for nitrogen and sulfur, but not for phosphorus and potassium. So restricting the root volume tends to have the biggest negative impact on nitrogen, and not so much on phosphorus and potassium. Calcium and magnesium. I call these elements, folks, cellular processors. And they're found in plants at really fairly high concentrations, 0.2 to 0.5% of the dry matter weight. Calcium is an element that's very important in cell division. Cell division at the meristem, at the growing point. Magnesium, of course, is the essential central component of the chlorophyll molecule, and that's what makes plants green, and that's what carries out photosynthesis. So they are very, very important macronutrients. But you know, folks, as a field crop fertility scientist, here in Western Canada especially, I never worry about calcium or magnesium being a limitation on production of plants growing in our prairie soils. The reason why is that our soils are very, very rich in calcium and magnesium. In fact, when you look at a soil profile, often you dig down, you see a whitish layer below the surface. That whitish layer is calcium carbonate. Our soils here, our prairie soils, have all kinds of carbonates. Calcium carbonate, magnesium carbonate, lots of calcium and magnesium, such that deficiencies of calcium and magnesium seldom, if ever, arise in production of plants out there on field soils in Saskatchewan, or the prairies for that matter. Probably the only place where I've seen, for example, magnesium deficiencies, sometimes in Ontario, southern Ontario, for example, they'll add magnesium to tobacco. and also in the Maritimes for potato production. But here in the prairies, lots and lots of calcium. But I can't forget about it if I'm talking to an audience that's using a growth medium or hydroponics, because you've got to have enough calcium and magnesium in there because they are critical. It's just that folks like me that work out in the field tend to forget about it a little bit. And finally, we have the essential micronutrients. Macronutrients, micronutrients. Micronutrients I define as those elements being required in small quantities. And what's the guideline, or what's the boundary between the two? Well, it's a little bit arbitrary. But generally, I think of micronutrients as being elements that are found in plants in part per million concentrations, rather than in percentage type values. But under this listing of micronutrients, I would include iron, manganese, copper, zinc, nickel, boron, chlorine, molybdenum. A lot of those, you know, folks, are metals. And also functional for some plants, but not all. And I don't think we could call these essential elements, but they do seem to play a role in metabolism of some plants. Sodium, which oftentimes we normally think of as a toxic element rather than that. But interesting, some plants like sugar beets, for example, do seem to require some sodium. Cobalt for nitrogen fixation by legumes, vanadium, and silicon. Silicon's kind of an interesting one. I don't think you're ever going to see a deficiency of silicon ever show up, and I don't think any of you would ever be adding silicon to your growth medium. Do you add silicon? No. But interestingly, silicon has been shown in the production of rice, I believe, to have some potential benefit from silicon fertilization. A couple of studies I looked back on to increase the straw strength or standability of rice. So, but certainly not an essential element. But these micronutrient elements here, folks, even though they're required in only a few parts per million in many cases in the plant, a deficiency of these elements will restrict, prevent growth as surely as a deficiency of a macronutrient. And they're involved, as I say, in a host of metabolic activities, activation of enzymes in the plants, electron transport, cell division. A good example is boron, which is an element that's very important in cell division at the meristem, the growing point. So boron-deficient plants will often have curled up, misshapen leaves and stems right at the very tip or apex of the plant. And these elements, these micronutrient elements, may be taken up by the plants as ions, but more often as chelates. And how many people in here use chelated micronutrient elements in their system? Yeah, okay. Chelated, and what chelated iron? Yeah. Very common. And what a chelate is a chelate is, for example, an iron atom that is complexed or bound to an organic molecule. And what the chelation does, which refers to the reaction of the organic molecule with the metal like iron, or it could be a chelated form of copper, chelated form of zinc. All of these chelated forms of these elements are available as actual fertilizers. What the chelation does is it renders that micronutrient element soluble and therefore available for uptake by the roots. And also some of these chelates are also used as foliar sprays as well, because plants can also absorb many of these micronutrient elements through the leaves as well, particularly when they're applied as chelates. So that's certainly chelation is important for these micronutrients, because some of these micronutrients will become very, very strongly sorbed. Just like I said, phosphorus will get stuck really tight to some soils, especially soils that have lots of carbonate minerals or are very acidic. Same with these micronutrient elements. Some soils, for example, copper and zinc at high pH, will become very tightly bound. And so that's particularly when a chelated form, for example, of iron or zinc may be very beneficial. Chelated form of iron or zinc to overcome this lime-induced chlorosis that you may see on high pH soils, a striping of the leaves that comes about from iron deficiency, and adding a chelated form of iron can be very beneficial in overcoming that. Finally, when it comes to micronutrients, folks, the last thing I'll say is that recognize that some of those micronutrients can be toxic at high concentration. In fact, for some of these microbes, there's a fine line between sufficiency and toxicity. And a good example of that is with boron. Boron is an element. You can apply it at a low rate if it's deficient, and you can have the plant will recover from that boron deficiency. The plant will take it up. But if you've got too much boron, you can very quickly run into a situation where that boron is toxic to that plant. And similarly, copper can also be potentially toxic if it's placed at high concentrations in the soil or the growth medium, especially if it's close to the seed. So be aware with these micronutrients. A little bit can be good, but a lot, in some cases, you can run into some rather severe toxicity issues. And boron is one good example, and I would say probably copper is another. So what happens when we don't get enough nutrient to the plant in the available form? Well, obviously, as we're well aware, that plant will suffer. And it will suffer both in the yield, and it will also suffer in the crop quality. And an example of that is, of course, when you don't have enough nitrogen, as I say, that's going to negatively impact the pounds per acre or kilograms per hectare of what you grow in terms of the yield, the mass produced, but it also has a negative effect on the quality. And nitrogen is directly related to protein content, as I said. In fact, the way that protein content is often measured in plant material, like grain, is by measuring the nitrogen content. So the way that you can get the best quality then, of course, is making sure that you've got the appropriate amount and balance of those nutrients to produce the kind of constituents like the proteins that give that crop its best qualities in terms of nutritional and even things like storage characteristics as well. A few pictures that I have here then, just to show you some deficiency symptoms. In this case, I don't have a lot of vegetable ones, a few, but of course you can see actually in terms of response, nitrogen is the element that tends to produce the greatest response in yield, as shown here in the case of a cereal crop growing in pots here in a growth chamber. No nitrogen fertilizer, nitrogen fertilized. You can see the classical symptoms of nitrogen deficiency there, folks. Spindly plants, the bottom leaves are turning yellow. Why the bottom leaves turn yellow with nitrogen deficiency? Well, nitrogen is mobile in the plant. So when the plant starts to run out of nitrogen, it takes it from the old leaves and moves it to the young leaves. And that's why those bottom leaves turn yellow and die. That's different than sulfur. Sulfur deficiency will also produce yellowing, or chlorosis we call it in the plant. But sulfur deficiency tends to show up in the young leaves, at the growing point, the youngest leaves, because sulfur is not mobile in the plant. The plant cannot move the sulfur from the old leaves to the young leaves where it needs it, so the young leaves show the yellow. Now, if you've got severe nitrogen and sulfur deficiency together, generally that whole plant will look yellow and spindly, and it's kind of hard to figure out really what's the main limitation there. But that yellowing associated with nitrogen deficiency on the old leaves, sulfur deficiency on the young leaves. Phosphorus. Now, this is canola. Brassicaceae crop. Use this as an example here, and unfortunately I didn't have any severe phosphorus deficiencies that I could pick out on any other cruciferate crops, but canola here, this is canola without phosphorus and with phosphorus. And you know, phosphorus deficiency is what I call a situation that really I would probably best or most aptly describe phosphorus deficiency as hidden hunger. Hidden hunger. Because in the majority of cases, phosphorus deficiency really doesn't produce any kind of really marked symptoms. Sometimes you see a little bit of purpling around the edges of the leaf, but most often, phosphorus deficiency, this is an extreme case of it here too, the plants are just shrimpy. They're unthrifty. They're small. But unless you got something to compare it to, oftentimes you don't really know that phosphorus is a limitation. And so phosphorus is a really hard one to sort out if it's actually a limitation in the growth of your plants, unless you've got a fertilized treatment to compare it to, or unless you're doing some type, maybe of example, a tissue test to actually confirm that that phosphorus level in that plant is below the critical level. But it has a huge effect, as you can see, on yield when it's deficient. Potassium deficiency, and showing this on canola again. It's an opportunity to work with some plants, and we're showing some very nice symptoms. This is potassium deficiency on canola, showing your very spindly, weak plants. If you've got plants that are tending to be falling over, flopping around, that may be a sign of potassium deficiency. Compared to these ones over here with good strong stems and stalks, the ability to stand up straight is really associated with an ample supply of potassium. This is a picture I have here of potassium deficiency on onions in the Fraser River Valley in BC. I took a few years ago. And I picked this because it shows very nicely potassium deficiency, kind of like phosphorus. It tends to be a bit of hidden hunger, kind of unthrifty. But one of the more characteristic symptoms of potassium deficiency, folks, is that the leaf tips will tend to become necrotic, yellow, brown, and that really shows up nicely here on these onions. So look for necrosis or deadening on the leaf tips, especially the bottom leaves, because potassium, like nitrogen, is mobile in the plant. Now, it's a little bit more difficult to pick out because, there's probably, 100 reasons why the bottom leaves of a plant would tend to turn brown and start to fall off, a lot related to disease, and potassium deficiency is only one of them. But it is a more or less characteristic symptom, this deadening of the leaf tips there. Sulfur deficiency tends to, and I show here again in canola, tends to show a kind of, whoops, I've lost there in that one. Let me go back here again. Oh, there we are. There. Okay. Sulfur deficiency, in addition to producing yellowing of the young leaves, oftentimes folks will produce a kind of curling or cupping of the leaves. You can see that cupping, curling, also some mottling. And in the case of brassicas, like rapeseed, mustard, canola, and others, I mentioned right at the beginning of my talk that brassicas, cruciferae, have a very high requirement for sulfur. And in fact, in some cases, adding nitrogen fertilizer without adding sulfur to a cruciferae crop, if you're interested in the actual seed yield, you can have an almost complete inhibition of seed yield in that cruciferae crop by adding excess nitrogen without sulfur. So the cruciferae are a group of plants that are very important to pay attention to this nitrogen-sulfur balance, as demonstrated here with the symptoms that you observe here on that canola plant. I blocked myself up. For some reason. Okay. Copper deficiency. Copper deficiency sometimes produces a kind of a melanosis. And as shown here, folks, on cereals, what copper deficiency will sometimes do on a monocot is it will cause that end of the leaf to twist up and kind of, we call it pigtailing, because as you can see there, it kind of looks like a pig's tail. And in addition to seeing that kind of pigtailing, as that crop will grow to maturity, sometimes the head, the reproductive portion, will take on a kind of brown or melanosis color as well, as another symptom of copper deficiency. I got it there before. This is a canola plant that is deficient in boron, folks, and one of the things that you can see here on this boron-deficient canola plant in particular, misshapen leaves, the upper part of that plant, the growth points kind of twisted, curled, malformed. So a characteristic symptom of boron deficiency often is tissue malformation at the growing point. And finally, toxicity oftentimes will show up, as shown here with radishes, growing on soils with different concentrations of nickel. Nickel is a micronutrient element at low concentrations, but at high concentrations, nickel can be toxic. And as shown there, going from control with no nickel to 80 to 160 parts per million of nickel, you see almost complete inhibition of that radish growth. And the other thing that you see, in this case in oats, that nickel toxicity shows up as a striping of the leaves. And you might say, well, why would nickel toxicity produce a striping of the leaves? Actually, what the nickel is doing is it's inhibiting the uptake of zinc by the plant. So actually what you're looking at there are classical symptoms of zinc deficiency, which are small leaves and a striping of the leaves. Basically, the interveinal areas are turning yellow. So that's kind of an overview of what those nutrients do in plants and a little bit about what deficiencies of them result in. Where do those available nutrient ions in plants actually come from? Well, in a soil or a potting medium, much, and I in fact would say most of the nutrient that the plant would actually take up during its growth cycle actually comes from reservoirs of nutrient in that soil, apart from what's already present in the soil water. So in terms of availability, what's in the soil water is immediately available typically, but we also have a reservoir of nutrient in that soil in the form of humus, the stuff that makes the soil black, that imparts that quality to that soil. Plant roots cannot directly take up nutrients in the organic form. So nutrients that are contained in humus, like nitrogen, must be converted into ammonium and nitrate by microorganisms in the soil. And we call this process, folks, mineralization.
I brought you a text, guys.
Oh, yeah. I can't seem to make it move ahead. So well, this gentleman's getting things tuned up again for me. So just to be aware that there are reservoirs of nutrients in the soil. A lot of nutrient can be held in the organic form, in, for example, the peat material that you're adding, in manures or compost, that slowly becomes available to that plant as it grows. And in order to make those nutrients, to render them available in those organic forms, that has to take place through the action of microorganisms. So microbial decomposition is required to turn that humus, that organic form of nutrient, into the forms like ammonium and nitrate that the plant can use.
I've got a question about that.
Absolutely. Good time for a question.
Sure. So we use a peat-based potting media.
Yep.
Professionally mixed.
Yep.
We don't do it at
Yep.
all.
Yep.
And we use constant injection, 2820 is our main feed.
Yep.
So what's being bound up by that peat? When is it released? If I'm constantly injecting, am I actually making use of anything that's being bound by the peat, or is all the nutrients coming from the solution?
I would say, I think probably a lot of that nutrient that's being taken up by the plant is coming from the solution. Although the peat may absorb some of that nutrient onto its surface, for example, it might even what we call bind up or immobilize some of that nutrient as it passes across and moves through it. The fact that you're continuing to add that nutrient solution would probably mean that the sorption capacity, the ability of that peat to sorb that nutrient, so to speak, would become saturated. So there would be some removed, but I wouldn't expect it to be a whole lot. And, if your nutrients in your solution started to run down, I do suspect that peat may be able to buffer that a little bit by releasing some from that solid phase into the solution where the roots can use it.
How much would you say that buffer capacity exists?
I don't have a good answer for that, sir, because it really depends a lot on what the actual source material of that peat is. Is it something that's really highly humified? Or is it, peat right from a surface of a peat deposit where I would expect actually it probably wouldn't sorb that much, and it actually might tend to tie up some nitrogen when it decomposed as opposed to liberated.
Our peat's quite fresh. It's not very...
It's not very humified, so to speak.
It's not very broken
Okay.
down. It's quite coarse fiber.
Okay, so in that case, I would expect that peat actually to have relatively little influence on supplying any available nitrogen or even tying any up, sir.
Okay.
Yeah. Oh, we're in business again. Sorry about that. I don't know what happened there. There's PowerPoint on the screen. Okay. The back of business, that's good. Yeah. So, I guess in question there was a nice question too. You know, what can we do to increase plant available nutrient ion supply? Basically, if there isn't enough nutrient coming out of that organic form in that media or coming off of where it's been sorbed to, of course, then we're looking at adding some type of an amendment. And indeed, you can even create, of course, a medium for your plant growth out of things like compost. Compost mixed with soil, and as we've heard about as well, peat mixed with soil or pure peat. So manures, compost, and other materials, of course, have only a small proportion of their nutrient in inorganic available forms. In fact, typical compost that we've worked with here in Saskatchewan, folks, we find that maybe on average only about 10% of, for example, the nitrogen in that compost is in the nitrate and ammonium form that the plant can immediately use. So in that compost, you are relying, if you're going to rely on it solely as a source of nutrient, you are relying on that material being broken down, decomposed by organisms in the soil in order to be rendered available. And the rate at which that occurs depends on the nature of that compost. It depends on the temperature, the moisture, as that influences the activity of the microorganisms in that soil. Now, there's one property that you can measure of a compost material that I think can give you a pretty good idea of how fast and to what extent it's going to release available nitrogen. And that property is called the carbon to nitrogen ratio. And labs out there, and lab in Saskatoon here, like ALS Labs, does manure analysis. For about $15 or $20, they will analyze your manure, and they can give you a carbon to nitrogen ratio of your manure or your compost. And generally, if the carbon to nitrogen ratio is less than about 20 to 1, when that compost or manure decomposes, you will get an almost immediate net increase or release of available nitrogen for your plants. But if it's a manure or compost, say it's a manure or compost that has a lot of straw mixed in it, or maybe it's a yard compost with a lot of leaves in there, if there's not much nitrogen in that compost, that is, if the C to N is greater than 30, you're probably going to see a lag in available nitrogen. In fact, if it's a wide enough or high enough C to N ratio, you, in fact, folks, may actually see a temporary decrease in available nitrogen before an increase. So I guess my advice is that if you are using manures or composts, you can get it tested for a few bucks, and you'll get a much better idea of what's in there, and you'll also get an idea of its availability. And of course, if you want to immediately increase the supply of available nutrients, you can add soluble commercial or mineral fertilizers. So products like urea, ammonium nitrate, ammonium sulfate, potassium sulfate, ammonium phosphates. Those are examples of fertilizers that all contain nutrient in soluble form. When you add a pellet of one of those fertilizers to your growth medium, within a few hours it will tend to completely dissolve, and all of those nutrient ions are released into the soil water, and they're available for plant uptake. Now recognize that some other fertilizer products, and I use an example, rock phosphate, a little bit different than those soluble fertilizer products like that. Rock phosphate is only partially soluble. And if something is not soluble, folks, it's not going to be plant available. And generally, as a rule, we say the greater the solubility of the fertilizer, the greater its availability for uptake, the more important it is and more effective it is as a short-term source of nutrient. But we recognize that those same soluble fertilizer forms, folks, if we put too much too close to the seed, we can injure. We can burn those plants. Because all fertilizers like those ones there, essentially they're salts. So when they dissolve in the soil water, they act like any other salt. They act to hold back the water from the germinating seed and seedling. And that's what produces, when you apply too much of it, what we call fertilizer burn. And that comes from that salt effect. And also for ammonium-containing or producing fertilizers like urea, we also get some injury from high concentrations of ammonia gas that are produced in the vicinity of that urea granule. So finally, how do you assess your plant's nutritional status? Well, we took a look at some visual symptoms out there, and they can certainly provide a good first indication. But I think a really powerful tool out there is tissue testing. Any folks in here use tissue testing? Okay. And a couple. So as a general, well, what are your folks' impressions of that? Has it been useful for you?
Yes.
Okay.
Very much so.
Very much so. Okay. Basically, you take a sample of that plant tissue, you send it to a lab, and they analyze the nutrient concentration. Now, in tissue testing, to do it properly, it is important that you do note and make record of, and indeed provide to the lab that you're sending the sample to, of course, the species of plant, but also the plant part that you sampled, the age of that plant, because those are all factors that influence the concentration of nutrient in the plant, apart from the availability in the medium. So you want to specify, provide as much information as you can. The lab will make the diagnosis, folks, by comparing the concentration in your plant material to what's called the critical or ideal nutrient concentration. And I often term that the CNC, the critical nutrient concentration. So just as an example, critical nutrient concentration of corn leaf at silking, so stage, plant part, opposite and below uppermost ear, 3% nitrogen, 0.3% P, 2% K. So if your N, P, and K concentration of your own corn leaf taken at silking, opposite and below the uppermost ear, is less than those values, then you're going to need to add fertilizer. You don't have enough. When it comes to making diagnosis based on critical nutrient concentrations, there's a pretty good database out there. Because it's not commonly, for example, done for vegetables in Western Canada, I'd say probably the database that we have here isn't as good as in some areas where vegetables where tissue testing is more common. It's most common here for field crops, small grains, cereals than it is. But I think as you, for example, would take a sample to a lab and ask for a tissue test, as the lab becomes aware of the demand for that service, they will seek out critical nutrient concentration data for the crops that you are interested in. And so it's a sort of a situation where as you demand it, it can be supplied. But I do have to say there's not a lot of tissue testing, I think, that goes on right now in Saskatchewan in vegetable production or ornamentals. But there's a lot of data out there worldwide that I think could be brought in. So I encourage people to use that as a tool. Maybe they might kind of give you a little bit of a funny look when you bring in a sample. Oh, gee, I don't know whether we can actually provide you with any type of interpretation. If they look, I think the information's out there, and I certainly think it's one way to encourage, stimulate the agencies out there that do tissue testing to provide that info.
ALS is great for that.
They're great? Okay, good. Excellent. So lab right here in town, ALS. Yeah. Excellent. The other way is to use a soil test, which is an analysis of soil conditions, including available nutrient content. Can be useful in assessing limitations on growth. So this is actually an ALS, a soil test report here, based on a soil analysis. And I use this as an example of what you get for $30 or $40 is you get all of the characteristics of your soil measured, the important ones like texture, the pH, the salinity, which is provided by a measurement of electrical conductivity, and you get all the available nutrient levels in that soil. And for the plant that you specify that you want to grow, using those available nutrient levels, folks, you get an idea of whether they're deficient, sufficient, even in excess or toxicity issues for nitrogen, phosphorus, potassium, sulfur, copper, manganese, zinc, boron, iron, and chloride. And in this case, this is for a vegetable garden, a recommendation for the rate of nitrogen, phosphorus, potassium, sulfur, and so on to apply. Now again, response, for example, of specific vegetables to fertilization in Saskatchewan, the database that they would use to recommend amounts, not as well developed as it is for small grains, field crops, but nonetheless, I think it's a good first start. And after you do this for a while, get your soil test levels, and maybe you've added some different rates of fertilizer to see what was going to happen, you can kind of start to generate your own set of data and response curves to added fertilizer, such that when you test again, really probably all that you might just look at are these numbers here, the levels of available nutrient in the soil, and start to develop your own set of, I guess, recommendations for fertilizer nutrient to add. So folks, I guess to conclude, by paying attention to contents of plant available nutrient in your growing medium, whatever that is, it may be soil, it may be some type of a potting mix. Indeed, it may even be a solution that you're adding in there in a kind of hydroponic setting. The content, the availability of those ions in the amendment, and monitoring the plant, I think, can be very useful in maximizing your production. And of course, not only the yield, but also the survival and indeed the quality of what you're producing as well. So I am going to stop there. I think I've just about used up my time, except for 5 minutes, and I'd like to open it up to folks for questions about nutrients, fertility, plant nutrition in general. Anybody have any questions or thoughts that I might have raised or?
Well, my
Yes.
question is, for different growing medias, I use 2 different growing medias combined. Am I inhibiting the stickiness of those nutrients, or am I increasing the availability to my plant?
And I guess it would depend if you're combining two different growth medias together. I guess it would depend on what you were combining together. In general, if you're combining highly humified organic material, or if you've got mineral material that is of a clay-sized fraction, the humified organic matter and the clay material will tend to absorb nutrients like phosphorus and potassium, and indeed some of those microelements, and bind them. If you're mixing, for example, a peat material that's pretty raw, or a compost that's maybe not highly humified, it's probably not going to have as big an influence on making those nutrients stick and stay in place. That being said, like I said, although some of those media may absorb those nutrient ions, it's an equilibrium that gets set up between the nutrients on the surface and the nutrients in solution. So I guess what I'm saying is they're not stuck there forever. So as the plant decreases the nutrient ion concentration in solution, nutrients will move off of that surface out into solution to replenish it. So you do want a few things in there that are going to stick those nutrients so that they don't leach out the bottom of your pot or your trays or your beds or whatever and end up running out if you end up applying a little bit too much water. I tend to think, it seems to me at least, and based on, is that a lot of the pre-made media out there do a pretty good job of supplying what is needed for the early stages of, for example, producing seedlings, bedding plants. And they'll grow for so long. But eventually, I know when I go and I look at those, you can see after they grow a very small volume of soil and a lot of growth there, you can start to see that they will start to especially run out of nitrogen. I see nitrogen deficiency symptoms first and worse, more so than seeing phosphorus deficiency on some of those plants that have grown a long time in a very small pocket or bed.
The other question I have is about canola and the phosphorus deficiency,
Yeah.
where they're spinning.
Yeah.
Can you reverse that in canola by adding phosphorus?
Yeah, absolutely. And I'm going to talk a little bit more about fertilization after the break here in my next session over in the vegetable component. But yes, for example, if you note deficiency in a growing plant, you can add nitrogen, and as long as you're not too late, earlier is better, but you can make applications to the growing plant and you'll get pretty decent recovery. For phosphorus, you can also add phosphorus. A foliar application, the plant will absorb a little bit of phosphorus through the leaves, but generally you're probably better putting that phosphorus right into the soil, but you will get some recovery from that. Also sulfur. In fact, sulfur, you can get very good recovery from sulfur deficiency applying it even very late in the growth cycle of that plant, because the plant tends to take up sulfur gradually over the season. Whereas a lot of those annually seeded plants, they need most of the nitrogen, phosphorus, and potassium early on. So you don't want to delay too much. But indeed, what I call post-emergent application can be very effective.
Temperature, how much of an effect on nutrient uptake does that have? Is it only on the immobile or is it on all of them? Or
Yeah, that's an excellent question. What's the impact of temperature on nutrient uptake, mobility, and uptake? And generally, we would say the colder the soil, the lower will be the mobility and uptake. But it does especially affect the immobile nutrients like phosphorus and potassium. So under very cold soil conditions, having some phosphorus and potassium close to where the roots of that germinating seed or seedling are going to be is very important to ensure early nutrition. And in fact, in the field crop production, we have a name for that. We call it a starter fertilizer, and the effect that it produces, we call it the pop-up effect, because having that P and K close to where those roots are going to be, especially under cold conditions where the diffusion rate of phosphorus and potassium is limited, where root growth is limited, having that phosphorus and potassium close to where that in the seed row or close by gives that plant a really good early start.
is it possible to burn if you put too much starter?
Absolutely, and I'm going to talk about that. I'll talk about that in my next session a little bit about the importance, especially in vegetable production, not having too much fertilizer in that seed row. You can burn your seeds with too much phosphorus fertilizer in the seed row, the same as you can with nitrogen fertilizer. It's just that the salt effect of phosphorus fertilizers is not as high as it is for a nitrogen fertilizer like ammonium nitrate or urea. So generally, safe rates of phosphorus are higher than they are for many nitrogen products. Potash, KCl, also has quite a high salt effect, so we do have limitations on safe rates of those that you could put close to the seed. So you do have to watch out if you are going to put fertilizer on. And unfortunately, those safe rates really haven't been worked out for vegetables very well compared to field crops. I've done lots and lots of work in canola and peas and lentils, but I've never done any work, for example, with carrots or beets or tomatoes. Yeah, maybe down the road.